Okay, dark energy, maybe the most profound problem in all of science today. Where did that slide come from? So this is a big one. So this is a wonderful problem, and I think this will give you a sense of the kind of problems that we feel lucky to be a part of as a scientist, because it's really big, and it's really confusing. And and we don't know if it'll be solved tomorrow. Well, I don't think it's going to be solved tomorrow, but you know what I mean. A year from now, 10 years from now, or sometimes we discover a problem accidentally sooner than we should, and it takes, 100 years to solve. Okay, so where were we left? We were left with the fact that it's well established that the expansion is speeding up, and we were left with this idea that, first of all, that Einstein's theory says that gravity can be repulsive. Not just the study of it, but gravity itself can be repulsive. And we were left with that nothing has repulsive gravity in the Zen sense. Nothing is not nothing, you remember all of that. And we were left with the sense that the experimenters found that the universe is speeding up, and the theorists found a really good explanation that was only off by 55 orders of magnitude. And it all has to do with how much nothing weighs. And, you're going to see all kinds of bets all over the place. Turner's theorem is nothing weighs nothing. So I can't prove it. Actually, I guess we were talking about mathematicians. That's Turner's conjecture. So this is fun. I mentioned this yesterday. This is what we live for. We start with one puzzle, and now we have two. So why does nothing weigh so little? That's that problem. And by the way, what's causing the universe to speed up? And of course, these two could be related. They might be unrelated. So that's what it's like at the frontiers of science. Okay. And then I showed you this slide yesterday, and this is, you can barely see this. This is a plot. This is how much matter there is, and so this is, the 27.3%. And if you pretend, if you assume that the dark energy, the stuff that's causing the universe to speed up, is just vacuum energy, which I also mentioned is known as Einstein's cosmological constant, that's a really good fit to the data. And so, some of you are going to say, what's the matter with you guys? Isn't lambda good enough? Lambda is the symbol for the cosmological constant. And so I want to explain why it's not good enough and why you're going to spend a little bit of money to find out what it is. And it's back to Eddington. We have no good theory for it. Why do we like these big problems? Why do the theorists like the big problems? Because they require a crazy new idea. It's not going to be some young graduate student comes back and says, Professor Turner, when you guys were calculating how much nothing weighs, in equation 4, the 2 should have been a pi and everything works out. It's not going to be that. It's going to be something that appears like a crazy idea, and I want everyone here to read this and sign a form saying you did read it. Not every crazy idea is a solution to a profound problem. Most crazy ideas are just crazy. Okay, so don't send me all your crazy ideas. So let me tell you about some of the crazy ideas. This is an extract. Oh, no, this is an interesting idea. This tells you how we think, how scientists think. So we talked about supersymmetry last time, that for every particle there's a supersymmetric partner. For every particle that has half integer spin, there's an integer spin particle. So if the world were supersymmetric, we can prove that the vacuum energy is 0. Okay. But the world is not supersymmetric today. And so maybe that explains why it's not 0, that if supersymmetry has anything to do with nature, it's what we call a broken symmetry. And so therefore, the fact that we don't see supersymmetry today and that the vacuum appears not to weigh a lot. Maybe those are related. Now, in practice, when we try to calculate what broken supersymmetry would predict for how much nothing would weigh, that's where the 10 to the 55 comes from. So it doesn't quite work. But, you know, maybe it's like Gamow, that, you know, we don't have all the right equations in the paper yet. Here's the extravagant idea. So those string theorists, you know, you got to admire them. You know, all those extra dimensions and all this and that. And so originally, do you all know this? Originally, string theory was motivated on the idea that it would be a unique theory. And it would be the only theory that the creator could choose. Now, if that isn't arrogance, they now admit that there's 10 to the 500 different versions of it. That's close to one. But what I really wanted to show here is it's called the cosmic landscape of string theory. And what's interesting about this is that these different points in energy space have a different vacuum energy. And mostly they're really, really big. But there's a lot of them, and one of them might be very close to zero. And so in order to explain why our vacuum energy is so close to zero, they posit another 10 to the 500. I'm not quite being fair, and so please don't tell Leonard Susskind that I said it that way, but it seems like a very extravagant solution, and I'm more worried about testability, which we'll come back to. You already saw this yesterday. When in doubt, we add a scalar field, and we're going to be even worse about this because the Higgs exists. And so you can also explain this with a rolling scalar field. And, so here's my crazy idea. So I'm the dark energy guy. I invented at least the word dark energy. There's no dark energy. You got to cover your bets here. It's a new aspect of gravity. And here it is. So I can explain this in words really, really well. It's almost as good as Einstein's equivalence principle. When the universe gets empty, it accelerates. Oh, that's really simple. And of course, well, you might say the universe isn't empty. Oh, just a second. As the universe has been evolving, you know, space has been getting bigger, the amount of matter has stayed the same, so the density of stuff in the universe has changed by 99 orders of magnitude. So it's really empty. Now, the good news is that this is beautifully simple. It fits on one transparency. When you set equations to it, it predicts a beautiful universe that accelerates when it's empty. Unfortunately, there's some small details that it does not predict, like the solar system. Who needs the solar system? But it could be that we have the wrong theory of gravity. It could be what the cosmic acceleration is all about, is that it's telling us that general relativity, which we already knew is not the final theory of gravity because it doesn't have quantum mechanics in it, needs to be replaced. Describing dark energy. So I really want to just say one thing here, and I had to say this somewhere, so I'll say it here. So the defining feature of dark energy is it's extremely elastic. We call that negative pressure. And it turns out in Einstein's theory, what causes gravity is both mass and energy and pressure, and that's how it gets repulsive gravity. And so, and this was much more relevant between 2000 and 2008. The symbol that we use to describe what dark energy is the ratio of its pressure to its energy density, and that's called W. Okay, a few smart people there. And so this is how we can distinguish between different brands of dark energy. So for example, vacuum energy has W equal -1. Some of these rolling scalar fields, W could be anywhere between -1 and 1. Some weird forms, W is -2/3. And what's interesting about W, the only reason I wanted to show this is the density, the energy density in dark matter. And if W is equal to -1 and it's vacuum energy, then it doesn't change with time, which makes sense. If it's an energy associated with the vacuum, then it shouldn't change with time. If W is not -1, it changes with time, and I'll come back with that in a second. So that's the way we can get at it. And so here's what we know about W so far. And again, don't be scared by this graph. Here's W. We know that W is minus 1.05 plus or minus 0.06. So it's real close to minus 1. But it might not be minus 1. So here are the two big questions. So does dark energy change with time? So that's a sort of a nicer way of saying, is W equal to minus 1? And that's something we can measure by studying the acceleration of the universe better. And we know that general relativity can accommodate cosmic acceleration, but does it? Maybe there's some test that'll show that it doesn't accommodate this acceleration. We can find a contradiction. And so there's an experiment that just had first light about 2 weeks ago. This is the 4-meter Blanco telescope on Cerro Tololo in Chile. And that telescope is going to be used for an instrument called the Dark Energy Survey. So it's going to be, well, they built a camera called the Dark Energy Camera. And they're going to do a survey to study dark energy, and they just had their first light, and they took a beautiful picture of a dark energy galaxy. Actually, it's just a galaxy. And then the South Pole Telescope has spent the past few years studying dark energy, and it's going to publish some results soon. And in the future, the Large Synoptic Survey Telescope and, I can't even talk about this, hopefully the United States will launch a telescope to study dark energy. We invented dark energy, we discovered dark energy, we followed Churchill's rules, about the Americans always get it right after exhausting all the other possibilities. So we went through about 12 designs and got a perfect design, and now the Europeans are going to do it, and we're thinking about not doing it. But that's, okay. Let me turn, that's my list of right questions. Let me turn to a couple of questions that are big, they're interesting, but according to me, they may not be right for progress, but they're big questions. And so, who knows, maybe one of these will be answered first. So this is Andrei Sakharov, people probably recognize him. Maybe some people know he was a physicist. And one thing, I talk all about where the dark matter came from. It came from the quark soup and this and that. And I'm not going to talk about where the atoms came from. But the atoms are a very interesting story. Maybe somebody will ask a question. But in 1967, Andrei Sakharov gave a seminar on April Fool's Day about, and so that's 1967. Remember, Turner and Cobb didn't arrive at Fermilab until '83. So that's when, the connections between particle physics and cosmology really got going. So he was way ahead of his time, and he gave this seminar that left everyone scratching their heads because he was worrying about cosmology. He was a particle physicist in addition to being an activist and a voice for human rights. And he talked about how the atoms could have evolved. And, well, he wasn't wearing this t-shirt. And it involves proton decay, the fact that protons may be unstable, that the laws of physics don't respect this, aren't the same for matter and antimatter. And and most of the equations were right. And we now think that his formula for why they're atoms is correct, but the details, the devil is in the details here, and I don't think this is a puzzle we're going to finish, but it's pretty important because this would explain where the atoms come from.